So example number 34, welcome back, 1.3 part 2. Example number 34 says evaluate the difference quotient for f of x equals x squared minus 3. Now that language, this is out of our book. It's not as clear as it could really be. I'm going to say, let's say find the difference quotient for this function, where what we're doing is we're doing our basically our slope formula using function notation. So that was our f of b minus f of a over b minus a. And I give you this little tip here about b squared minus a squared equaling b plus a times b minus a little factoring trick, because we'll see as we work on this problem, we're going to need that tip. So let's first of all figure out what f of b might look like for this function. I'm going to maybe make a little table over here to the right where I have x and f of x. Now I'm going to plug in a for x, and I can see that my function just says square and then subtract 3. So a squared minus 3 would be the output for a. And if I input a b and work out x squared minus 3, I get b squared minus 3. That's the beautiful thing about functions, is they're predictable. You plug something in, you know what's going to happen. All right, so now this is what I'm going to use. This table is what I'm going to use in my slope formula, my function, my difference quotient, my average rate of change. So f of b turned out to be b squared minus 3. And then I have to subtract f of a. Now careful here, using parentheses is a really good idea because we want to make sure we subtract all of f of a. And then on the bottom, just b minus a. So careful with that negative sign, that's going to distribute. Let's rewrite that. We get b squared minus 3 minus a squared, and then subtracting negative 3 turns into adding 3. Still over b minus a. And then very nicely, we subtract 3 on the top, add 3 on the top. Those 3's are gone, and we are left with the expression b squared minus a squared over b minus a. Now careful, it's so tempting to just cancel b squared and b, cancel a squared and somehow get a b minus a left over. But we want to always, always, always factor before reducing or canceling anything like this, any sort of expression work. We want to factor before canceling. So that's where this tip comes in. So b squared minus a squared, difference of squares, you might remember is b plus a times b minus a. It makes a difference that the b squared is first. And then over b minus a, now I am allowed to cancel that factor of b minus a. And my final answer here is just b plus a. So that was a totally abstract exercise. But what's happening is now I know that if I take any 2 points on that parabola, remember that parabola that we had, a and b, if I just know what the x coordinate a and the x2 coordinate b, I can now find that slope by adding those two values. That seems kind of mysterious. So that's the slope between x equals a and x equals b. Okay. So here's now a little more concrete example, possibly, rather than just arbitrarily 2 points floating in space. So exercise number 117, the function v of t equals 340t over t plus 3 gives the speed in miles per hour. So that's our output, v of t. We get out a miles per hour of a dragster at each second t, that's our input, seconds, during a quarter-mile race. Find the average rate of change in speed from the first second to the 8th second. So I see those words, average rate of change. I'm just thinking slope. Here's a diagram that was in our book. Over to the right, we've got time as our horizontal axis with seconds, t counting across the bottom. And then we've got our speed in miles per hour is our output, our y-axis. And the curved pink line is a graph of that v of t equals 340t over t plus 3. And the blue straight line is the line that is connecting t equals 1 to t equals 8. So we're going from t to equals 1 to t equals 8. The slope of the blue line is the average rate of change from the function from t equals 1 to t equals 8. So we've got our two input values. What we don't have are output values. So I'm going to start by making a little table, t and v of t. Input t equals 1, we'll have to calculate the output, and input t equals 8, we'll have to calculate the output. Now careful here if you're using your calculator, because we're adding on the bottom of that fraction, you could just do it in your head when we plug in 1, 340 times 1 over 1 plus 3. But if you want to type it in as is, not worry about 1 plus 3 being 4, make sure you use parentheses around that 1 plus 3 before you calculate. I got 85. That means after 1 second of travel, this dragster is going 85 miles per hour after 1 second. That's pretty amazing. And then after 8 seconds, we'll put in the 340 times 8 this time, and then on the bottom we have to take 8 plus 3. And I'm not sure if this comes out to a whole number or not, but again, careful with parentheses when you plug this in. And I did not get a whole number this time. I got about 247. I'm going to call that 0.3. Round it off to maybe 1 decimal place. We could have maybe rounded it to 247. And looking over the graph, notice how what we found are the y values at t equals 1. 85 seems reasonable. And at t equals 8, we're very, very close to 250. That looks very much like what we have on the graph. All right, so average rate of change in the speed is the slope. So now we'll do our calculation. 247 or 247.3, depending on how accurate you want to be, minus the 85, and then divide by 8 minus 1. Again, if you want to do all of that at once on your calculator, use parentheses. You can do 8 minus 1 in your head if you like, and then just divide by 7. Kind of your call, how you want to work that out. But it is really important that you do be able to get some kind of a number. So from these numbers, with my choice of rounding, I'm getting m equals 23.2. Now for units, this one's a little tricky to write about because the output units, remember, these were miles per hour. This vehicle's going 250 miles per hour almost after 8 seconds, and the input is seconds. So this would be, the slope here would be the output units, miles per hour per input units second. So in other words, this dragster is increasing its speed by, on an average of 23.2 miles per hour for every second. That'll get it from its 85 mile per hour mark at 1 second, progress through those seconds, going up by 23 miles per hour per second, each of those 7 steps up to 8 seconds, and you will land at 247 miles per hour for a final speed. So there's an example of using slope to get an average. But you can see from the graph, it's actually going faster at the beginning. It's increasing faster with that initial launch from its starting point, and then it's still going faster and faster, but not nearly as quickly later on. All right, take a breath. We've got one more topic to look at. This one's kind of involved. I think I'll actually break that into a part 3 on this video set. So I'll come back for part 3.